Before we introduce the Cauchy integral formula, we're going to have to introduce the concept of chains and cycles. And these are pretty simple objects. You just take a formal sum of curves. So capital gamma here will just be this formal sum of gamma 1 through gamma n, where gamma 1 through gamma n are just some curves. And this is just a way of defining an integral over a bunch of curves at once. But we do allow some extra flexibility in here, so we'll allow maybe you could put in reverses of curves in here, and then that would be reflected in the sum here as well. So if I follow, I could follow gamma 1 and maybe the reverse of gamma 2, and I get this, this sort of nice formal way of combining curves that directly corresponds to an algebraic formula with the integrals. So this is what chains are, and then a cycle is just a chain that's built entirely out of loops. And then we can define the winding number of a cycle just to be the sum of the winding numbers of the loops inside it. And you would only do this for z's not in the union of the actual sets on which the curves live, and this is what we would call capital gamma star. So examples of chains and cycles, I mean, I can have, so here's a loop, and I would just have, you know, some formal combination of these would be a cycle, and I can compute integrals over this and winding numbers. So I could compute a winding number with respect to a point here. And in this picture, I guess since this is the only curve that goes around it, it'd have a winding number 1. But maybe this point, I guess it has this curve going around it and this curve going around it. So I'd have a winding number of 2 here with respect to this cycle. And I guess I drew these cycles all going counterclockwise, but you don't have to. I could throw one in there that goes the opposite direction. That's no big deal. And so a point right here would have winding number 0 because this curve goes around it counterclockwise and this one goes around it clockwise, and so on. But this will just be mostly a convenient way to write out the Cauchy integral formula. All right, so here it is. It's very big. So this ultimate Cauchy integral formula will be stated as follows. So let U be a domain, and let capital gamma be a cycle. So again, just a formal sum of a bunch of loops. But you could also have multiple copies of the same loop, or you could have negative copies of the same loop. And assume that the winding number of the cycle is 0 for all z's not in the domain. And this will be, you'd sort of count gamma as equivalent to 0 in this case, or homologous to 0. And we'll see a related notion in a moment, but let's state the theorem. So let F be analytic on this domain U. Then we get our version of the Cauchy integral formula here. So this integral that looks very similar to what we've been calling the Cauchy integral formula over this cycle. So f of w over w minus z with respect to dw over 2 pi I will be equal to how many times the cycle, let's see, I wrote this all wrong. Let me fix this. So this part is not, shouldn't involve f. Let's see, it'd be the winding number of z with respect to gamma. So it's the number of times that gamma winds around z times the value of f at z. And so you usually recover the Cauchy integral formula on a circle from this because the circle will wind around the points inside at one time, and so you would just get f of z here. And you could also recover our Koshi integral formula for an annulus because we would have an outer circle and an inner circle going the opposite way. And our Cauchy integral formula on an annulus had the integral along this circle minus the integral going this way, which you could encode with chains as maybe the boundary of the outer circle minus the boundary of the inner circle. And that's the chain that you would integrate over. And notice this would satisfy the hypotheses above because, let's see, if I'm having an annulus where I remove this part and I remove everything outside this disk, then the winding numbers inside here, well, I'm counting this inner circle as going clockwise because of this minus sign. So you'd get on the inside, the winding number here with respect to this piece would be -1, then its winding number with respect to this piece would be 1. So inside it winds around points 0 times, and then out here it's winding around stuff 0 times. So it satisfies the hypotheses here, and then you see that you'd get our usual Cauchy integral formula for an annulus. Which was this difference like so for z's in an annulus centered at z0. Okay, and then we also get out of this what's usually just called Cauchy's theorem, that in this setup the integral of just f alone along this chain will be 0, and that follows from replacing the f above here, replace that f with f of w times w minus z, so you get the cancellation here, but then when you evaluate this at z, you get 0. And then finally, this last piece follows from this piece here. If I have two cycles here in U, and the winding numbers are the same for all points outside of the domain, then you get that these line integrals along the cycles are the same, and that's just because the way we do this algebra on cycles is just like so. And the algebra on the cycles is completely formal, but it just transfers to the usual algebra you'd expect with respect to integrals. So this condition here would just mean that the winding numbers of this difference would satisfy the condition up above, and so it would follow from this second part of the theorem. And so if we have this condition here, that the winding numbers are the same for all z's outside the domain, then we'd say that gamma 1 and gamma 2 are homologous. Okay, and in the next video, we'll start going through the proof of this Cauchy integral formula.